Welcome back. In this next series of videos, what we're going to do is do an example to illustrate how top-down design could be applied. So in order for that to work, we're really going to need a larger example, something bigger than anything we've done before, so we can sort of justify the different techniques that we're going to apply in order to make top-down design work. And so what we'll do is work on an example based on the Pong video game, which is really one of the first video games ever created back in 1972. Now, as you can see in Pong, it's sort of a virtual table tennis match where you have two paddles that move up and down and a little square ball that goes back and forth. And the idea is that you have to prevent the ball from going off the other edge of the screen. We're going to do something called SoloPong. And in SoloPong, the idea will be that we'll have just one player, one paddle, and three walls instead of just two. So now the ball will bounce off all three walls and will stay in play as long as we keep the paddle and the ball in contact. In other words, as long as we keep hitting the ball. If we miss, then the ball will go off the screen on the east side and we'll be done. So, a good place to start in this situation is to think about what methods we're going to need at a very high level. So if we represent our whole video game, SoloPong, as this box, right now, just based on the knowledge that we know, if you've read the text, you know that we need three methods. The setup method, obviously, to set up and initialize all of our graphics and just to set up the shape of the screen, all that. The draw method, which will display everything that's on the screen. And since the paddle moves with the mouse, we'll need to have a mouse moved method in order to keep track of the paddle. Before we start further decomposing those methods, though, let's take a look at what variables we're going to need in order to make this program work. So these will be things that control how everything moves, how we know if things run into each other, where things are, all that. So we're going to, at the very least, have variables for the ball, the paddle, and the walls. So let's go ahead and go to the whiteboard and start looking at what variables we might need for each of those items. Okay, we're going to represent our ball with a square, just to keep things very simple. And so one of the things we'll need to track is the size of that ball. So we'll establish a constant ball size, which is the size on an edge of that ball. We know in processing, in order to know where to draw the rectangle that's going to represent the ball, we'll need to know the center point of that rectangle. So we're going to have two variables that represent that center point. So that will be ball X and ball Y. And then finally we need to know how fast the ball is moving. Every time the display window refreshes, the ball will move a little bit, and that will make it appear to glide smoothly around the screen. So we're going to need to have two variables that represent the speed in the X and the Y direction. Okay? So in the X direction, we'll call the speed in the X direction delta X, and we'll call the speed in the Y direction delta Y. And those may be positive or negative. Those will determine how that ball moves around. Okay, so there's our variables and constants for the ball. Each wall will also be represented as a rectangle. And so we're going to assume that we're looking at the north wall. It will just be as wide as the screen, so we don't really need a separate variable for that. We'll use the width value. But we will need to have something that tells us how tall the wall is. And so we'll establish a constant called wall thickness that tells us how thick a wall is. Then we need to know the coordinates of the center of that rectangle, just like we needed to know the coordinates of the ball. So we'll call that north wall x, north wall y. Those will be the coordinates of the center of that rectangle. Now the other thing we're going to need to know is sort of the coordinates, or at least the y coordinate in this case, of an imaginary line for when the ball collides with the wall. So if you imagine that the ball is here, that shows where the ball is when it runs into the wall, and its center, which is what we're using to track its coordinates, is not yet to the wall. So we need to have some sort of a value here that tells us how far down that imaginary line is to look at the collisions. So we'll call that north call y, for the north collision y value. And that way we can look at the coordinates of the ball, in particular the y value, and determine when it's actually run into that north wall. If we wait till this value reaches the wall, then the ball will be halfway off the screen. Now the third thing we're going to need variables for is our paddle in SoloPong. So this is another rectangle, and so it will need some of the similar variables that we've seen so far. We're going to need to know how wide it is, so we'll have a constant there. Oops, sorry, that should be width. We're going to need to know how tall it is. That will be our panel height constant. We're going to need to know where the center of that panel or paddle is. So that will be at paddle x and paddle y coordinates. Now, we don't have to have delta x and delta y for the paddle because it doesn't move on its own. It'll be controlled by mouse movement. Now what we need to know then is where are the collisions possible, okay? So let's draw our imaginary ball in several locations. One where it's contacting the paddle, one where it just misses low, and one where it just misses high. And again, what counts is the center point of the paddle in each position. So we're going to have an imaginary line that runs up and down here, okay? And that will be called our paddle collision x value. Okay, that will help us determine if the ball hits coming from this direction or not. And then we'll have to have two imaginary lines down here, which are our cutoffs for hitting too low or too high. Okay, so paddle call bottom y for the bottom paddle collision coordinate. And similarly up here, paddle call top y. That's the coordinate for that spot up there. Okay, so again, what those imaginary lines do is let us determine whether the ball hits the paddle or not before it actually goes inside the paddle. Okay, so now let's take all those variables and put them together into a class diagram. Okay, now that we've looked at all the variables that we'll need, or at least most of them, we're going to summarize them in our first draft of a UML class diagram for our SoloPong application. So remember the format of the class diagram. Up at the top is the name of the program that we're working on, SoloPong. In the middle is our listing of all of our class variables. Local variables and for loop variables and things aren't listed. And down below is a section with our methods. So we have setup, draw, and mouse moved so far. And up here we have variables that we just discussed. Most of the ones that we looked at are on here. Notice that we have also tripled the number of wall variables because we have 3 walls. And also notice that the north and south collision lines need a y coordinate, whereas the west wall needs an x coordinate because the ball will be moving in a different direction. And really the only other thing that's different in here is the color of the ball and the background. Okay? Ball color will also be used for the walls. So this summarizes the data that we have to do. In our next video then we'll start to look at how do we decompose these methods with our top-down design procedure. So, see you then.